preparing the the YouTube is live now. Go ahead.
Okay, perfect. So hi everyone. Following this RC interaction, I will talk a bit about waves and their interaction with both the ocean and the atmosphere, and give you a quick introduction to waves and to wave modeling, in particular with WaveWatch and its coupling with CROCO. So this talk took large input from Fabrice Ardouin presentation, so I would like to acknowledge him over there. So waves have numerous interactions with the atmosphere, the ocean, and the ocean crust, as can be pictured on this sketch. So there are really numerous interactions. I will go through some of that. So first, we can name RC interactions. Obviously, when there are waves, the surface is not flat, and waves can generate aerosol production through sea spray. They also have a strong implication in RC flux of momentum and heat. And there are strong implications for remote sensing too. So from satellite altimetry, we can measure wave height, but also thanks to waves, we can measure other properties such, for example, currents or winds. Waves also have interaction with the ocean circulation and mixing. The first interaction that we can talk about is the Stokes drift. So what is Stokes drift? It's the fact that when waves are generated over an ocean with an underlying current, the orbital motion of the waves are not closed due to the underlying currents. And this induces a transport that can be significant up to 10-meter depth on average. And if we average vertically this transport, it is actually balanced by the mean current transport. But this is only the case when the flow wave interaction is balanced. So when the wave had just been generated by the wind, it is not balanced and there is the residual drift. Waves also implies stuff about ocean mixing, so through wave breaking and wave turbulent interaction. And they can generate like what we call Langmuir circulation. So that's this relatively large horizontal vertical circulation that is due to the interaction of the wave-induced transport and the mean flow. And this usually arises when the wind blows steadily over the ocean surface. And all this impact on ocean circulation and mixing have consequent impact on biology, drifters, or dispersions of pollutants and stuff like that. Waves also have interaction with the ocean sea ice. Indeed, waves can propagate through the sea ice and induce mechanical forces in the sea ice that can, for example, help breaking it. But also the sea ice have impact on waves, limiting their propagation and dissipating them. When we come closer to the coastal zone and to the near shore, there are obviously very strong interaction between waves and the circulation. Waves start to fill the bottom, and also they can break eventually. So they really drive the surf zone dynamics. They have an influence on the bottom boundary layer and on the sediment transport. And you will have a talk tomorrow about that in more details. And they can induce setup and storm surge. Finally, waves also have an impact on the ocean crust. They induce microseisms that can be recorded by land-based instruments, for instance. And on a practical way, of course, there are interest in studying waves and modeling them for engineering, like offshore structures, for maritime transport, and for the modeling and evaluation of drifting objects and pollutants. So now, what are waves and how do we represent them? We can think of waves as these large crests that we see from the seashore. But there are also numerous really shorter wavelets riding on the large waves that makes this complex sea state as a superimposition of different kinds of waves. So waves are usually characterized by a few key parameters. That is the wavelength, which is the distance between two crests, or the wave period, which is the time between two crests passing at a fixed point, or the significant wave height, which represents part of the energy. So here on this sketch, you have a representation of the different kind of waves as a function of their wavelengths, going from capillary waves up to tidal waves. And in green here, you have their main forcing to degenerate them. So as we have seen, waves, C-state is complex and with multiple wave systems. So we usually represent the C-state using spectrum, energy spectrum of the waves. And on this spectrum, as a function of a period of frequency, we can see 3 peaks of waves, of different kind of waves. So we have infragravity waves, a peak of swell, and Wincy peak at a higher frequency. And this spectrum really represents the distribution of the variance across the different scales. It also provides the definition of the significant wave height, which is computed as 4 times the root mean square of the integral of this spectrum. And this is an important parameter that we use a lot in wave modeling and wave assessment. So waves are not static, of course. So they energy propagate, that propagate at a velocity, which is the group velocity plus the current speed. And the group velocity is different for each spectral component. Waves also turn. They follow grid circles around the globe, and they can turn with refraction when the effective phase speed is changing. Also, waves show, that is, they're shorten and becoming higher when the water depth is changing or when they encounter a change in the current velocity. And finally, when they become too steep, wave break. So we can see that waves have implications at very different scales, going from really the turbulence scales up to the climate scale. And so we can imagine that this is not easy to represent all these scales in modeling. So we will talk about spectral models, which are kind of models that doesn't resolve each wave evolution individually, which cannot be done on a global simulation, for example, or even a relatively large area simulation. So these models, what do? They solve the equation of evolution of the wave spectrum, that is that at each longitude-latitude point of the grid, there is a spectral space separated in a given number of directions and frequencies, and we solve the evolution of the energy at each direction and each frequency of this spectrum. So here is an example of a spectrum that we can have with WaveWatch that represents several wave systems. So here we have 4 different wave systems. A wave system toward the north with a wavelength of at about 150 meters, a higher, a longer wave system toward the east, and 2 wave systems with really that are closer to Wincy with shorter wavelengths. So the wave model solves this wave spectrum evolution, and using this quantity that is named n here, which is the wave density or the action of the spectrum. It's actually another way to measure energy. It's just a more general invariant of wave energy, and the correspondence between wave energy and wave action is provided on the equation on the bottom over there. So for solving this equation, there is an advection part, of course, and in this advection part, there is the influence of the ocean current, for example, and there is also a source term part, which is divided in several components, as can be detailed over there. For example, these source terms will represent different effects, such as generation by the wind, nonlinear wave-wave interactions, dissipation due to breaking or to bottom friction, scattering, reflection, etc. So they are kind of an important part of wave modeling, and not that easy to parameterize. So just to talk a bit about wave modeling accuracy. So what drives the accuracy of wave models? First, there are forcing parameters. I'm speaking there about winds, current, bottom, sea ice, etc. And wind errors are among the main source of wave model errors. So this is something to keep in mind. Currents can also be very important and can create a relatively large difference depending on the area. I will talk about that a bit more later. Then there is the choice of parameterization, obviously, and there are a lot of parameterization in wave models, especially the source term parameterization, which is quite complex and which tuning can be a bit tricky. And of course, modal numerics, so the level of accuracy that we have in solving the equation. Maybe just a word on model validation. So usually we can perform validation against available data. And in our case, it's usually satellite altimetry that can measure significant wave height, or eventually buoys, but there are not very numerous. And now we have new satellites existing that can measure the wave spectrum, but it's clearly a bit more tricky. And at the moment, the most commonly used validation is significant wave height. So output of wave models are obviously the full spectra, which is the prognostic variable of the model. But it's kind of large output. So usually it's not output at every time step that we want, or every point even. We can also have just a frequency spectra, so it's integrated in direction. And we can have what we can call bulk parameters that are derived from the spectrum. So it can be significant wave height, mean direction or mean period and stuff like that, or parameters that are provided by the forcings or the source terms. So maybe a bit more in practice now. So WaveWatch, as I said, does not solve the density of wave equation, but it doesn't solve it in once, but it is split into 3 parts. So we have an advection part, a refraction part, and a source term part. And because of that, we have different time steps in the model. It is a bit like for CROCO, we have the barotropic mode and the baroclinic mode. So we have 2 different time steps. For WaveWatch, we have 3 different time steps, actually 4, because there is a global time step, but it depends on the other ones. And these different time steps have to be set accordingly to their constraints. So we have the global time step, and here I provide some guidance to set these time steps. So the global time step will be 2 to 3 times the CFL time steps, which is the second one actually. The CFL time step depends on the advection. So there is a condition on which we have, it's usually 3–4% of delta X, but you can compute it properly with this little formula. Then there is a refraction time step that has to be chosen carefully when there are strong currents, for example. And then there is a source term time step, which is usually between 1 and 10 seconds, depending on the forcing. Then in WaveWatch, after choosing time step, you have to choose all the numerical settings and parameterization. And for that, there are 2 steps. First, a step that is named switch. It's pre-compilation settings, so like the CPPD keys in CROCO, and they are chosen before compilation. Then once this is chosen, you can compile, and then you can eventually set some other parameters. So in these different keys for compilation, there are the propagation scheme, the generation and dissipation parameterization, the wave-wave interactions, and etc. And also some setting about coupling. So we will talk about this a bit more later. Then you can change some parameters of the parameterization through name list. And the main name list for that is named the WaveWatch3 grid.inp file. And in this one, you can set some parameters depending on the parameterization that you have chosen. There is a quite well written manual for WaveWatch for that to go a bit deeper into that. So WaveWatch can run on different type of grids, going from structured grid, so it's rectangular grids or curvilinear grids. There is an example here of a global grid, and we can use with this structure grid a multi-grid option. It's like nesting in CROCO. If you have already used agrif, it's not nesting with agrif, but it's another kind of nesting. And it allows to, for example, here build a global grid with a regional grid over the Pacific and even other smaller grids around region of interest. It's quite easy to manage actually, and there are nice tools provided for that. WaveWatch also provide unstructured grid facilities, and so it's kind of easy to manipulate the WaveWatch code with these different kind of grids because it's kind of transparent using the WaveWatch model. But the only thing that is really changing is the way you build the grid before using WaveWatch. So WaveWatch 3 requires three grid definitions to run. Of course, we need the bathymetry to define the grid. Then we need the Lancy mask, of course. And there is a third thing that is quite important. It's the obstruction. So it's a way to account for subgrid scale island, for example. So when an island is not solved by the grid because it's too coarse, we can use these obstructions to account for the decay of energy of waves when crossing these subgrid islands. So two types of reference data are usually used to build these grids. So there are so global high resolution bathymetry can be used, so GEPCO, eTopo bathymetry. Global shoreline database, which is GSHHS. So this allows to draw the coastline, also to compute the obstructions. And there is a kind of nice package named GridGen available to pre-process all this stuff to build the grids. Forcing, of course, the waves need forcing to be run. So we need atmosphere forcing, for example. Eventually, we need current forcing, water level evolution, and ice forcings. So all these forcings are not mandatory. The model can run without it, but obviously, if you don't blow wind on the surface, it won't propagate waves. And this forcing can be prescribed from realistic condition using also a sort of pre-processing tool. And otherwise, you can prescribe a constant condition for sensitivity or idealized tests, for example. Then there are the boundary conditions. So if you're running a regional simulation, you want waves incoming at the boundaries. And so for that, there are also tools provided to prepare boundaries that have to be prescribed with another model output, global model output in the form of wave spectra. And finally, initialization, of course, for each model we need initialization. So it can be from a previous run or otherwise from calm conditions, so no waves, basically, or from an idealized wave field generated by an idealized spectrum. So here is the workflow of the WaveWatch model. It seems not very easy, but actually it's pretty usual stuff like every model. So first we have the grid executable that allow to build the grid. So you have to provide a name list, so the grid.inp name list, which provides settings on the grids. And it will output a binary file named moddef.wavewatch3, which is the grid settings. Then you can use the start executable, which will build the initial condition. Eventually, it's not in a frame here, but you can use what is named the PRNC executable, which help building realistic wind forcing and current forcing conditions. And finally, the main program of WaveWatch is the shell, which is basically the model and the time stepping and everything. So this shell is where you run WaveWatch. And this, so all the input files are .inp are name lists. Then all the .wavewatch3 files are binary files generated by pre-processing routines or by the shell. And then there is a few utilities to convert these binary files to netcdf files, for example, for the outputs. So now if we go to coupling, so we want eventually to couple at an atmospheric model with a wave model and an ocean model. So in our case, it will be processed with the coupler named Oasis. And Lionel will give a talk a bit later on how Oasis work and the philosophy of coupling around that. But just to give you a few teasing about that, so we have exchange of a few variables between the three models, 2 by 2. And we can see that there are quite a lot of variables that we can exchange. And regarding the waves, actually, we can send the Charnock parameter, which is used to compute the RC fluxes, to the atmospheric model. And to the ocean model, we will exchange bulk wave parameters such as significant wave height, mean period, mean direction, and the momentum flux from the waves to the oceans. And we can eventually also exchange quantities that are such as the Stokes drift and the Bernoulli head pressure, which I told a bit about earlier. But also some of these variables can be computed within the CROCO model directly. In practice, how to couple WaveWatch with CROCO. So within WaveWatch, you need to activate some switches. It's the pre-compilation keys I've talked about earlier. So you need to activate these different keys that are Q, Oasis, and OIZOCM or OIZACM for the ocean wave or ocean atmosphere coupling. And you need to be in MPI. Then in the shell.inp, which is the name list for WaveWatch, you need to activate coupling with a flag, which is this C letter in front of water levels or current or winds, depending on what you want to couple. And finally, And finally, you need to define the coupling time step in the shell.imp namelist too. So you will see that during the tutorial and during Lionel's talk a bit later. So you need to set up the exchange variables in the Oasis namelist too. And you have to change eventually, so the grid and the shell, you have to run the grid and the shell. So we have seen that coupling is a lot. Before going into coupling, I suggest that you really think about why you want to couple with waves or with the atmosphere. So I will just review a few situations in which coupling really does matter. So yes, waves are influenced by winds. Of course, they're generated by winds. They are also influenced by current, water level, and bottom roughness. And they are influenced by sea ice, and they have feedbacks. So they feed back to the surface roughness, they modify the wind stress, they generate current and modify the water level and the bottom roughness, they enhance mixing, and they can break up the ice and push it around, for example. So such feedbacks need to have a coupling. And here are a few, here is back to this, one of these complicated schemes about RC interaction. So yes, it's complicated and we need coupling for that, but only when it's matter. So here is an example where actually, yes, coupling matter. It's the computation of the RC momentum fluxes and especially the drag. So the drag coefficient is the way to parameterize the exchange at the surface, notably due to the roughness that is generated by the waves. So usually we have parameterization of this roughness as a function of wind speed. So here are represented a lot of existing parameterization of the drag coefficient as a function of the wind speed at 10 meters. And we can see that there is a large variety of parameterization. Notably, the very large variety exists at high wind speed, that is usually in tropical cyclones and very high winds of storms. And there, the wave state is very complicated, and we can see that, yes, there is a need for coupling, but also it's a place where wave models can struggle too. So it's kind of a tricky part. And we can see that even before this complicated 30 area of high winds, there is still a significant variance of the drag coefficient, which is represented on the bottom plot as a function of wave age. So the different colors are the different wave age, that is, are the waves young, so that is, they have been just generated not a long time ago, or are they quite older? So it's basically swell, so well-formed waves which have a different impact on the drag coefficient. So for that, of course, it matters coupling with waves. Then for computation of all the RC fluxes, of course, it matters. And when we have really chaotic or changing sea states, it's important to take into account for computing the momentum flux at the Earth interface, heat flux, and when accounting for interaction with sea ice. Then regarding the ocean component, there are really feedback to mixing and to circulation in the ocean that I've already introduced. And here is an example of a paper from Kuhl et al. 2020. So on the right plot, you can see the difference of turbulent kinetic energy between a run with and without coupling with the waves. So we can see that it's kind of important in some regions, for example, the circumpolar current or the North Atlantic. And this has to be accounted for. And on the left, you can see the correspondent mixed layer depths for different sensitivity tests on the most important parameters in wave current interactions. So yeah, there are also important stuff about that, but it depends on what the region you are working on and what is the resolution you are working on. Here is another example of importance of wave current interaction. It's where we have strong ocean gradients. On the left here, you have the mean significant wave height gradient, and you can see that it's very similar pattern to the mean geostrophic current vorticity that is on the bottom. So clearly, where we have strong current and current gradients, we have strong change in wave height. And this is also what is illustrated on the right, where we can see that on the right, we have the vorticity of the Agulhas return current on a snapshot. And then we have the change, the HS, so the significant wave height that really followed the path of the mean flow of the Agulhas retroflexion current. And so we can say that clearly it's important. And on the bottom curve, you can see that in black, we have altimetry data, so observations of the significant wave height. In blue, you have the model with current interaction. So it's kind of fairly representing the variation of the altimetry signal. And in red, you have the model without current interaction. So only wave watch, not accounting for currents. And you can see that it's clearly smoother and not representing the higher frequency and higher wavelength variations. Finally, when coming to the coastal dynamics, of course, waves are essential. Actually, they are really driving the nearshore dynamics. So we definitely need to have them. Indeed, they really feel the bottom. Their height is close to the ocean depth high. And so there are clearly very interesting interaction and driven circulation. So the water level is evolving. There is an impact of current on the wave evolution and a driving circulation from the waves to the currents. There is enhanced mixing. There is bottom streaming, and I've lost it. Sorry. Don't know what happened. It was the last slide anyway. But so yeah, going near shore, for sure, you need waves. But you will see tomorrow a presentation by Rachid Ben Sila that will talk a bit more about nearshore dynamics and the importance of that for sediment transport mainly. So finally, just a few links and references. So definitely there is the documentation section on the website and the tutorial coupling that is available all the time. And I think you really need to go through that because it's kind of a tricky part to go to coupling. And here are the few references that you can go to look at waves and their interaction with the atmosphere and the ocean. I think I was a bit shorter than the 45 minutes, but maybe quite dense. So don't hesitate if you have any questions.
Thank you, Swen. Questions? No, I do have one. I understand there's plenty of the development of wave models is for open ocean. And so you have a well-developed wave field. What can you tell us from the limitations of models like WaveWatch in, for example, the fjord area of Chile, or a fjord, some place where you have very short fetch?
Yeah, actually, there, of course, the model is more commonly used for global simulation or hindcat, so it's really well validated in this kind of situation. In regional cases, actually, we have kind of also a lot of use of WaveWatch. Maybe it will depend on the resolution, but even there, we have kind of a lot of configurations. And regarding short fetches, there were developments for example, for the Mediterranean Sea or for the Great Lakes in the US or stuff like that. So they have, usually they bring different parameterization for the source terms, which has really the tricky part in the wave model, because it's a slight balance between wave generation and wave dissipation. So this is in general one of the most field where improvements are made, and also nonlinear wave interactions is the other one. But there are actually works on short fetches areas. For Chile, for instance, I don't know, because actually you will have waves from the Southern Ocean coming, and so these ones are kind of well resolved. So you can have bias, but they will be associated to the generation bias of the waves in the Southern Ocean mainly, or eventually to the way that waves are dissipated along their propagation towards Chile, regarding swells, I mean. And if you have offshore blowing winds, yeah, this is maybe a situation where you have to look at the model a bit carefully and maybe change the source term parameterization to be more realistic about that. But there are studies about that.
There's one. Joseph?
Hi, Jullien. Thank you very much for your talk. I was wondering whether WaveWatch 3 could be used to, or maybe in combination with CROCO, model, let's say, flooding in a coastal area, or maybe a storm surge modeling. Could it be used for that?
Yeah, for storm surge modeling, actually, you need for instance, CROCO, you need a storm surge model because it's a hydrodynamics, it's not waves, and you have waves inputs that will be used to compute the storm surge. But storm surge is a combination of the atmospheric surge, so the pressure effect, and the wind stress effect too, and then the setup, which is actually the wave effect. So yes, you can compute surge using a coupled model, of course.
Okay, thank you.
In the chat, we have a couple questions.
Yes.
Um,
So first question was feedbacks on the meridional overturning circulation. I won't give an answer to that because I haven't studied that in particular, but I guess we can say probably yes. Then the significance of this impact, I don't know, because it can be impacting in different ways. First, the stress. So if we change the waves and notably the RC flux parameterization through the drag coefficient, we will change, of course, the circulation, even at large time scales. And the other one is the mixing, of course, and the way the waves and the current will interact and change the mixing. So probably yes. Then it will depend on climate models or large-scale Bayesian models. We have a tuning also of the parameterization without accounting for waves. But if you include more physics, so that is including waves interaction, you will have to probably carefully look at your simulation, but it should be better. We add some physics, so I guess it should be better, but this have to be looked at. Then there was another question regarding OpenMP parallelization, and I think not. I have to check with the development team of WaveWatch, but like that, I would, I don't know, actually, I have to ask them. Usually I'm using it with MPI parallelization, but I will ask them for sure. And then there was the last question regarding the use of scatterometer like CFOSAT data to validate the wave model. So CFOSAT data, yes, they are quite new. So, and they had some problems until not a long time ago. But there are studies starting to look at, of course, at wave and the validation against CFOSAT, which provide a spectrum of waves. So we have directional waves, which is very interesting because it's we didn't had that before with other altimeters. And so there are some studies. There is a special issue actually that will be delivered soon in GJR Ocean. So I think that maybe there will be interesting results about that. On my side, I haven't verified really the wave feedbacks with and without current using CFOSAT data for the moment. So I can't answer exactly this question. Maybe another interesting stuff to note that besides CFOSAT, there is another instrument that can retrieve wave spectrum. It's the SAR instrument on board, for example, Sentinel-1. But honestly, it's not easy data to use and to process, but they really give a nice spectrum in some conditions. So it's something to keep in mind if you really want to go further in the validation of the wave model on some areas.
Anyone else? Joseph?
So, sorry, I had a quick one. So back to the validation question. So basically, it's tricky to use satellite data because they are not as accurate as you get to the coast. What is the main problem with using satellite to validate wave parameters?
It will depend on which satellite data, but for altimetry, actually, there are data are quite good actually. With altimetry, so you will have significant wave height. One problem can be really close to the coast. Indeed, you can have problems, but it's only when the satellite fly from the coast to the ocean. In this case, you will have contamination from the coast, but on the other way, if you have a track where the satellite fly from the ocean to the coast, it's not that bad actually. It's quite good, quite close to the coast. It's important to know that.
Okay.
And regarding other satellites data that we have for waves, so for instance, for SAR data, so Sentinel-1, for example, data, in this case, cost is not a problem at all. It's a satellite and an instrument that is, they can provide an image of the coast, so you can see the continent really clearly on that and the wave field around. But the thing is processing of that. So you have a nice image, of course, then you have to work on that because if you want to avoid looking at the continent. So you have to mask part of the image and retrieve the spectrum on the other part, but the spectrum will be good really close to the coast. Honestly, I've looked at data in atolls or lagoons, and you can see the barrier reef and you can see the waves inside the lagoon. So it's pretty amazing for that. But it needs processing, careful processing of the data then. And regarding CFOSat, there are 2 existing products. So the usual full spectrum product cannot be used close to the coast because it's a 70 by 70 kilometer, something like that, square. So obviously, if there is coast or land inside that, you cannot use it. But there will be also soon, I think, available another product, which is a bit different and a bit more specific, which is it's a 1D spectrum. So you have this frequency spectrum on each beam of CFOSat. And with this spectrum, so you can go really closer to the coast because the footprint is really lower. But it's kind of also specific data. When you go to satellite data, for specific purpose, you need to really go deep inside that on the technical parts.
Thank you very much.
You're welcome.
Well, thank you, Swen. Let's wait then. Just make a break for 18 minutes to start at the hour. And I will stop.